So the first talk today, final day of ICBS, is by Professor Wen Qiang. He's going to tell us about partial entanglement network and geometry reconstruction in AdS CFT.
Okay. Okay. All right. I'm going to talk about some recent work on the so-called geometrical reconstruction in AdS CFT based on the so-called partial entanglement entropy. Okay. This work was done together with my the postdoctors Lin Zhou and Lu Yizhou and the other graduate student from USDC, Qiang Wen, based on these papers. The outline of this talk is I first introduce the holographic entanglement entropy, and then what is the partial entanglement entropy and its geometric picture, which I call the PEE stress. And then I'm going to talk about how to use the PEE stress to reconstruct or reproduce the entanglement entities for single intervals and spherical regions in higher dimensions. And then jump to multi-intervals and non-spherical regions in higher dimensions and introduce the new concept called the weight of the PEE stress. And in the end, I'm going to talk about our formula to reproduce entanglement entropy with the so-called Crofton formula in mathematics. It seems that our prescription, in some sense, reproduced the Crofton formula in the case of AdS space. Okay. The AdS CFT correspondence claims that some non-gravitational quantum field series is due to string theory involving gravitational dynamics. So you have some model that explicitly shows this duality in string theory. And if you take some limit, then for example, the strong coupling or Lux limit, then the string theory reduces to some supergravity. For example, in this case, in original paper of Marcina. And then it was soon realized that this duality can apply to more general asymptotic AdS spacetimes, which is that the d-dimensional conformal field theory could be due to some d+1 dimensional asymptotic AdS spacetime. So there are lots of evidences to show this duality holds, including symmetries and correlation functions and entropy quantities calculated in both sides of the duality and match exactly with each other in under this limit. What I'm going to focus on is the entanglement entropy in this duality. The entanglement entropy in a quantum system is defined in the following. For example, if you consider some quantum state of a system and split it into two subsets A and its complement, then you can define the so-called reduced density matrix. This is the original density matrix of the pure state, and you trace the degrees of freedom outside A, and you get some reduced density matrix, which could be considered as how a local observer who can only measure the information inside this subregion A, and this local observer feels that this local region should be in this mixed state, which is just the reduced density matrix. And then you can you calculate the Molloy entropy of this reduced density matrix, and you find that this value is defined as the entanglement entropy between the region A and its complement. This entanglement entropy captures the amount of entanglement between A and its complement. Last property is that if A and A and its complement is in a product state, which means that they have no correlation, then this entanglement vanishes. Okay, then we go to the AdS CFT correspondence and consider the entanglement entropy on the boundary on the dual CFT. For example, in this case, this horizontal line means the boundary where the CFT lives, and the region in lower half, in the lower side of this line is the corresponding AdS space. And if you calculate the entanglement entropy of some interval on the CFT, it will holographically be given by some minimal surface in the AdS block that is homologous to this boundary interval A, which is this is the celebrated Ryu-Takanagi formula, which tells you this. The formula is an extension of the fixed Hawking entropy. So this picture can extend to higher dimensions, and you can consider a higher dimensional conformal field theory on this plane. And on the right side is the corresponding AdS space, and consider an arbitrary boundary region on the CFT side, and calculate its entanglement entropy. And again, this entanglement entropy of this region A is given by the area of the minimal surface that is homologous to the boundary interval A. So this formula is quite simple and quite general in the large C limit. This is a signal of the correspondence between both geometry and the boundary, the quantum entanglement on the boundary field theory. Okay. This formula was later proved by Mondesina and Luckowitz, and the quantum correction version is also proved. And this Ryu-Takanagi formula has some interesting phase transition, which still gives us new inspiration in the study of holography, even in very recent. For example, if you consider the entanglement entropy of two intervals, there are two phases depending on the size of A1, A2, and their distances. And these are two different set of points of the external surface homologous to this boundary region, and you should choose the one that gives you a smaller entanglement entropy. This has some field theory calculation on proof for this picture by taking large C limit, with calculating the entanglement entropy of two intervals, and take large C limit. You can see the phase transition also on the phase on the field theory side. This picture also gives us inspiration in our study this topic. Okay. Then what do I mean by geometrical reconstruction? In this talk, by geometrical reconstruction, we interpret both geometrical quantities in terms of boundary quantum information quantities, or more explicitly in terms of boundary entanglement structure. So there are long history of this geometrical reconstruction. First is the black hole horizon, which is interpreted as the entropy of the black hole system. And then its extension, the RT formula, which interpreted the RT surface as the entanglement entropy of some boundary region. And then you can go beyond this extremal surfaces to some arbitrary, for example, in AdS3, you can consider some arbitrary line, Bach curves in the bar. And how to interpret the length of a Bach curve, you can use the so-called differential entropy developed by these people. And then also you can give some representation of the RT surface in the AdS part using the so-called piecewise, which also gives inspiration in our work. And also the tensor network as some some model to simulate the AdS spark, where you can reproduce the RT formula and other features of AdS CFT. You can see this is the differential entropy, and in the AdS spark, you consider some arbitrary curve. For example, this is some convex loop in the park. How do you interpret the length of this curve? You can use the RT surfaces, the set of RT surfaces that is tangent to this curve, and eventually you find that the length of this loop can be interpreted as some differential formula of a boundary entanglement entropy of single intervals, which that is why you call it the differential entropy. And on this is the piecewise picture. There's some assumption that in the bark there are on the boundary the CFT system is just a bunch of EPR pairs which are maximally entangled to each other, and this EPR pairs are represented by the bark threads, and the RT surface actually is some bottleneck from this boundary region to its complement. So you need to optimize the flow picture in the bark, and gives a max flow from this boundary region under consideration to its complement, and the max flux then that through the bottleneck is claimed to capture the entanglement entropy. And this picture is the so-called tensor network model of AdS CFT. You use some tensor network to simulate the bark space. Interesting, it can reproduce the RT formula. For example, you consider some interval on the boundary, which is a discrete interval, not in the continuous limit. You calculate the entanglement entropy of this interval. You are going to consider some homological curve in the network that cut the network with minimal number of costs. Actually, this minimal number of costs is, in some sense, the same as the minimal surface in the RT surface. Okay, this is some previous picture that inspires our prescription. Okay, let's get into the new concept of the so-called partial entanglement entropy and the so-called PV threads. The partial entanglement entropy is something new. The feature of this quantity is that this quantity describes some correlation between two space-like subregions, and the key feature of this quantity is that the quantity satisfies the so-called additivity. So which makes this description extremely simple. For example, if you consider the so-called the partial entanglement between some region A and the B union C, of course these subregions are all not overlap with each other. The correlation, the PE between A and the BC equals to the PE between A and the B plus the PE between A and C. And then there are also other physical requirements for this quantity, for example, the permutation symmetry, and this key property of normalization, which is that the partial entanglement entropy between A and its complement should reproduce the entanglement entropy of A. And the positivity and the upper bound and the invariance under local unitary transformations inside A or B, and this correlation structure of partial entanglement entropy should respect the symmetry of this system. Okay, actually there's no fundamental mathematical way to define this partial entanglement entropy in terms of the density matrix, but in many cases there are some way to find the solution to this bunch of physical requirements, and more interestingly, in some simple and important cases, you can find the unique solution to this set of physical requirements, which makes this set of requirements that just the definition of the partial entanglement entropy. Okay, this was done previously by Cassini and Huerta in a very early paper, but in that paper they refer the quantity that satisfies this set of requirements as the mutual information, maybe. But in our paper, we don't treat it as mutual information, because in many cases this set of requirements has solution, but it does not coincide with mutual information. So it's something else. Okay. How this partial entanglement we describe the entanglement structure of a system. So due to this additivity property, you can always decompose these regions into smaller regions, and then smaller and smaller until each site in the system. So eventually, this partial entanglement structure is described by two-point partial entanglement entropy, between actually two-point partial entanglement. So the PE between A and B is just a summation of two-point PE, where I is inside A and J is inside B. This is a discrete system. And in a collinear system, for example, in a conformal field theory or under quantum field theories, the PV is just a twofold integration of this two-point PV. This IX Y is just the P between the site X and the site Y. And the entanglement entropy should be reduced by this PE under the limit that B goes to the complement of A. And in quantum field theories, you need to take some regularization, such that the A and A bar, their boundary are separated by some infinite small term sigma. Okay, but this requirement is only imposed for spherical regions. Okay, I need to emphasize this. This normalization requirement only imposed to spherical regions. Otherwise, this set of requirements does not have a solution. Okay. Okay, there's some way to construct the solution to this function. What? You can think this as some starting point or definition. Okay. Okay. Actually, this property 2 to 7 are also satisfied by the mutual information. So this is why in the original paper, Cassini and Hurst take the solution as a mutual information. Okay. Okay. This is a quite general way to construct a solution to this set of requirements, but this only applies to two-dimensional systems. Two-dimensional space-time systems with one space dimension. For example, in a line, the degree spread is set in a line, and you consider a single interval on the line, and then you decompose it into three subregions: alpha L, alpha, and alpha R. This is together it makes the interval A under consideration. You can calculate the partial entanglement between the middle region alpha and the complement of A, the black part. It can be written as some linear combination of entanglement entities. The first one is the entanglement entropy of alpha with its left subset alpha L. The second term is alpha, the entanglement entropy of alpha with its right subset alpha R, minus alpha L minus the entanglement of alpha R. Okay, I can show that this linear combination actually is additive. For example, if you split alpha into alpha A union alpha B, for example, alpha A is on the left and alpha B is on the right, then you use similar formula to construct the partial entanglement between alpha A and A bar. And the first term is alpha A and its left subset alpha L, and the second term is alpha A and its right subset. In this case, the right subset is no longer alpha R because there's also alpha B is on the right hand side. So this is the right subset alpha B union alpha R, and minus is left subset alpha L and the right subset alpha B union alpha R. And similarly, you can also calculate the partial entanglement between alpha B and A bar, and then you get a similar linear combination. And if you add them together, you find that there's cancellations between this term and this term and this term and this term, and eventually you get S alpha L, this is alpha, S alpha alpha R minus S alpha L minus S alpha R, which reproduces this linear combination. And this, you find that this linear combination actually satisfies the additivity property. And they use some general properties of entanglement entropy. You will assume that this linear combination also satisfies all the rest of the requirements. So this construction is quite general. In two-dimensional, it does not depend on explicit series of the system. But the only requirement is that all the degrees freedom should lie in some order, unique order. If the order is not unique, then this definition is ambiguous. Okay. This is in two-dimensional. It's circled. It's okay. You can yeah. But if it is settled in two circles, then you don't know how to put the other circle as left or right. So then the definition is ambiguous. Okay. Actually, this quantity is indeed a conditional matrix information. Okay. So in generic two-dimensional series, where all the degrees of freedom are settled with a natural order, then you will have some unique way to construct the solution of these requirements. And also in higher dimensions, if the system has very big symmetry, for example, rotation symmetry, and such that the entanglement structure only vary along one-dimensional, one spatial direction, then you can construct the PE structure in a similar way. But how about in more generic cases? Actually, Cassini and Huerta in their original paper already talked about this solution problem. They found that in higher dimensions, if the series or if the state is with some Poincare symmetry, then the solution will be unique. And if the series has further symmetry like conformal symmetry, then they can give an explicit formula for this Poincare entanglement entity structure. Okay, so this is what we want to study: the vacuum states of CFTs on a plane, which deals to Poincare AdS space-time in general dimensions. So in two-dimensional CFT, the 2-point PE is just given by this simple value. And in general dimensions, it's also given by this value, which looks very like some 2-point function. And Poincare entanglement is just, again, just an integration of this 2-point PE, where X is in the A region and Y is in the B region. C is the center charge. This C is center charge of the CFT. Because you have some normalization requirement, which is that when B goes to a bar, you need to reproduce the entanglement entropy, which is proportional to this C. So when you impose all the requirements, you get the formula as the coefficient, which is just the center charge of the homomorphic area. Okay. Then with the boundary Poincare entanglement structure given, we want to geometrize this structure, Poincare entanglement. So, for example, in a global AdS3 on a time slice, the boundary is the CFT, and the first step is to interpret the 2-point PE where the Borg geodesics. For example, if you consider this X and Y 2-point PE, this Poincare entanglement between these 2 points is represented by this the Borg geodesic that connecting these 2 bounded points. So essentially, you get some network of geodesics in the Borg, which just looks like this picture. Okay, if you study in different models of AdS CFT, you see this kind of picture quite constantly. And in higher dimensions, this the CFT is of this this plane, and this dot is boundary degrees freedom, and you just represent this 2-point PE with this geodesic. And in the back also you get some network of the geodesics. Okay, so you could keep in mind that in the back it's just a bunch of geodesics, or a set of all geodesics that come out from the boundary and go back to the boundary. But only for boundary areas. Okay. Then you can represent this this buffer entanglement. Okay, I call this geodesics the PE threads. Okay, the PE threads. Then you consider the PE threads that emanating from some boundary point X, which is this geodesics, and you want to represent this. Use some mathematical formula to describe this this bunch of geodesics. Actually, you can use some vector field to describe this set of geodesics, where this tau is along the bulk geodesics that emanating from this boundary point. And this norm is not determined yet. This norm can be considered as some coefficient that describe the density of the PE threads. So the next step is to make this claim that the PE between A and the B actually is captured by the number of PE threads that connecting A and B. This is the second claim. Okay, with these two claims, you can totally determine the PE thread configuration in the bar. All the rest we need to do is to determine this norm. So you can consider this simple case. For example, if you consider the PE between the dot X and some infinitesimal segment d sigma y, then according to this claim, this Ix and the d sigma y, which is the PE between d sigma y and X, we can write it in this way because this PE is some continuous function and the d sigma y is infinitesimally small, so you can write it in this way. This should be given by the number of PE threads that connecting X and the d sigma y, which can be computed by considering the flux from X point to d sigma y. Of course, this vector field is divergenceless, so the stress in the bulk is conserved. You can take some arbitrary cross section of this between these two depth curves. For example, you can consider some semicircle centered at X, and then calculate this flux of PE threads that passing through this, and this equation should hold in any dimension, but only on in any dimension. And okay, because this is known to us, and this Vx is only one unknown parameter, which is norm, and n is also known to us, and this is the normal vector of this blue curve, and everything is known except the norm. So you can solve this norm from this equation, and then you get a complete description of this vector field. Of course, you have introduced some additional information, which is the direction of this threads, but you should keep in mind that we don't have this such kind of information because because you use some vector field to describe this threads. It in some sense give you some redundant information, which is just this orientation of the threads. Okay. Of course, right. It's not universal, right? And then if you calculate the entanglement entropy, it just tells you that when B goes to A bar, the entanglement entropy is just the number of PE threads that's connecting A and A bar. So you just consider this boundary interval A and compute all the threads that come out from A and to A bar. Of course, you can do some calculation, like you want to superpose all the. Okay, this is the solution. After we impose this requirements, you get the solution in AdS3. So the vector field in the part that emanating from some point O, which I choose this O as origin point, and the Q is an arbitrary path point, is given by this. D is the direction here, and the R is direction, horizontal direction. O is A is the interval, and O is the middle point. Okay. Okay. If you want to count this number from the number of threads from A to A bar, actually you just do some superposition of this vector field emanating from any point, because there's translation symmetry, so they looks the same. It's up to some translation. So you superpose, do a summation of all this vector field that's coming out from A, and you get some new vector field, which tells you the new vector field can be described as these integral curves. And you do some explicit calculation, you will find that the summation of all the vector fields that coming out from the region A will tell you that the strength of this vector field at the RT surface is exactly 1 over 4G that multiplies the normal vector. So if you want to calculate the number of threads that coming out from A to A bar, you just calculate the flux of this union, the summation of vector fields, and calculate the flux of this vector field that passes through this RT surface. You find that integrate around this RT surface, it exactly gives you the area of this RT surface over 4G. So this is just the entanglement. This which is minimal surface of okay, because this vector field is divergent, so actually you can calculate after you do a summation of this vector field is still divergent. So you can choose an arbitrary surface and give the same answer. But actually, as I told you, that this orientation of the threads is some redundant information. We have this result because we used this orientation of the threads, which is always coming out from A to A bar. If you don't use this orientation information, you just have some network in the bar with no directions. And if you choose some different paths for the same interval, I mean different homologous surface for a single interval, actually the number of threads that's passing through this homologous is different, because you have, for example, in this picture, if you have orientation, then these threads from this point to this point and this point to this point cancels with each other. But if you don't consider the orientation, then it will not cancel. It will not cancel. So if it cancels, then you get some divergent vector field, which is independent of the choice of this homologous surface. But if it does not cancel, then it will depend. So the key is to we will not use this orientation information later. Okay, this is actually not related to our results, because this picture is in fact the B-thread picture proposed by Heydrich and Friedman. So for this single interval cases, you can reproduce their result. For example, there's a group of people that proposed the B-thread picture around for geodesics, and our results exactly reproduce their results in general dimensions. Okay. Also, in higher dimensions, you can solve this vector field that coming out at the bit threads coming out from point O at any point Q, which is this vector field. It seems that there's only two components, because we have choose the angular parameters to all set to 0, because they're rotation symmetry. So you can choose set of the angles, and the other two directions is written this way. Okay, you can also do the summation. For example, if you consider static spherical region, you can also consider a summation of these vector flows by summing over all the points inside inside the spherical region. You also get some bitstress flow for spherical regions. And the key is that for these bitstress pictures, you always find that the bitstress flow at the RT surface equals to 1 over 4G. So this description reproduces the RT formula. But how about non-spherical regions and the multi-intervals? The answer is that for multi-intervals and non-spherical regions, the summation of these vector fields by summing over O in the region A does not give you the bitstress picture. So this picture only works for spherical regions or single intervals. How does this happen? How does this happen? So let's go to the simplest case of multi-interval. You will find that the key is to erase the orientation information of those threads. Okay. If you start from the two interval, for example, A is A1 union A2, and its complement is described by B, which is B1 and B2. And if the RT surface in this space is the blue curve is the RT surface, then the entanglement of A is given by the entanglement of B1 at the entanglement of B2. And also, you can use our results of single intervals, which is just counting the number of PE threads between B1 and its complement and the B2 and its complement. And then you split these two PEs into smaller pieces using the property of additivity. So you get that this, you write this second line to the first line. So this is PE between A1 and the B1 union B2 and the A2 union B1 union B2 plus 2 times the PE between B1 and B2. Okay, this is just using the additivity of this property of this PE. Okay, you find that the first two terms already gives you the PE between A and A bar. This is the original normalization property we have imposed. So A bar should be reproduced as A. And also this is something confused Cassini and Fullerton in their original paper. So the first two terms already gives you the PE between A and A bar, but there are two additional terms, the PE between B1 and B2. In normal sense, this PE between B1 and B2 is some correlation for outside degrees of freedom, because both B1 and B2 are not inside A. So in general, people think this kind of correlation does not contribute to the entanglement entropy between A and the B. But the RT formula shows that the entanglement entropy of A is not only consists of this A bar, but also some correlation between B1 and B2. Then you look at the PE thread picture, you will find that all the threads coming out from A to B only intersect with RT surface once, with this term, and also intersect with once. And the threads from B1 and B2 will intersect with the RT surface twice. And those inner threads from A to A does not intersect with this RT surface, so they don't show up in this linear combination. So it seems that whether any two-point PE contributed to the entanglement entropy depends on whether this corresponding PE threads intersect with the RT surface or not. And there is weight of this contribution. If it intersects with the RT surface twice, it should have coefficient 2. Okay, this is some basic assumption. Then we talk about the different phase, which is the RT surface become these two circles, and the entanglement is disconnected. So in this case, the RT formula tells you that S entanglement of A is given by SA1 plus SA2. And you can also use the our single interval results. SA1 equals to IA1, the PE between A1 and its complement, and the PE between A2 and its complement. These are single intervals. We can use our previous results. And then we also use additivity and write these two terms in the first line. So in the first two terms, it's also already I between A and A bar, and there's additional term to multiply the PE between A1 and A2. Then you look at this thread picture. The threads from A1 to A2 now intersect with RT surface twice. And this P1 from P2, P1 to P2 does not intersect with new RT surface. So this formula changes from this to IB1, B2 to A1, A2. So okay, this assumption works in this new phase, different phase. Then you can consider more complicated cases. For example, you think three disconnected intervals A1, A2, A3, and consider a configuration that RT surface is given by this three semicircles. And the RT formula tells you that this given by the entanglement interval A is given by SA1 plus SP2 plus SA2, B2, A3. And you use the single interval results to write this entanglement as the power entanglement this. And then you split into the first line. Okay, you will find that the threads that come out from A1 to B1, B3 only intersect with the RT surface ones, so the coefficient is exactly 1. And from A1 to A2, A3, intersect with RT surface twice, so there's coefficient 2. And from A1 to B2, it intersects with the RT surface for 3 times. You have coefficient 3. Okay, you just look at all the PE threads and count the number of intersections. You get some formula like this. So you will find that this first line and the second line coincide with each other by applying the additivity property. Okay, so it seems that this prescription works for any choice of boundary regions. Okay, if this curve has some orientation, then the flux, for example, the flux intersect with RT surface twice will give you 0 flux because it comes in and then goes out. But if you erase those orientation information, it has non-zero contribution. So the key is to erase those orientation information. We just consider some big PE threads in part with no direction. And the count is intersectional number with the RT surface. So okay, in some sense you get, given the RT formula, you get some equivalent description of the entanglement entropy, okay, with the RT formula. Okay, but in higher dimensions things becomes more complicated. In higher dimensions, if the boundary region is non-spherical, in higher dimensions, you have some threads inner threads that intersect with the RT surface twice. Also, some outer threads intersect with the RT surface twice or more times. So, for higher dimensions and non-spherical regions, the simple description of dual summation of all the threads coming out from some boundary region A to its complement does not reproduce the RT surface, but only for spherical regions. Because for spherical regions, all the threads only intersect with the RT surface once. So the flux equals to the number of intersections. Okay, then we go one step further. What if we do not know the RT surface in advance? So if you don't know which is RT surface, you don't know how to count the intersections, number of intersections. Then for some boundary interval A, you you start from some arbitrary homologous surface, and you want to calculate the number of intersections between this homologous surface and the bulk stress network. For example, there's a network in the bulk, and if you some network in the bulk, and this is our region A, and you consider some arbitrary homologous surface, and count the number of intersections between the homologous surface and this bulk network. Actually, there are some threads that for example, this kind of thread intersect with this homologous surface for 3 times, and this intersect with it for 1 time, and this intersect with this homologous surface for 0 times. So given this homologous surface, you can always count the number of threads from X to Y, and the number of intersections with this homologous is given by the omega. And this is the weight of this thread. And you multiply this weight with this the value of the 2-point PEV, and do a summation. Then you get the number of intersections between this bulk homologous surface and this bulk PE thread. Note that this 2-point PE gives you the density of the PE threads. So essentially, this formula calculating the intersection numbers between this homologous surface and the bulk network. And that's a coefficient of 1/2 because you do the integration of X and Y on the whole boundary. So they're double counting because the thread from X to Y and Y to X is the same one. So this is 1/2. So the conjecture is that you do some optimization among all possible homologous surfaces and found the one that intersects with the bulk network with the minimum number of intersections. So this minimum value will give you the entanglement of 8. But this formula is formidable to calculate because you cannot count all the number of intersections for each thread. That will be impossible to complete. But in fact, this calculation can be done along this homologous surface. So actually, you are calculating, you do an integration along this homologous surface, and for each segment on the homologous surface, actually you are consider the vector flow from all the boundary points at this segment. But you need to take an absolute value. This step is to erase the orientation direction of this threads, because when you are given with some vector field, you always have some orientation, and you do an absolute value, you erase this orientation information, and each thread that pass through this d sigma A will contribute positively. You do a superposition of all the X. For example, we just all possible threads that coming out from the boundary that passing through this segment is given by an integration of this value. And again, you need some coefficient of 1/2 because this X integration is over the whole boundary. So the threads that coming from this point and the threads coming out from this point actually is the same thread. So there's a double counting problem. So then, because this vector field is known, and then you can this integration is possible to carry out. So you first calculate the threads that intersect with this area element, and then integrate over this sigma A. And this calculation actually equals to the previous one. So we just evaluate this integration and minimize it by choosing all possible homologous surface. Okay, the interesting is that for any segment of this homologous surface, this first integration always gives you a constant value, which is 1 over 4g. Actually, you can prove this in the following. You can consider some area element, infinitesimal area element on the RT surface for any spherical region. Okay. Now this RT surface is some hemisphere in the bar, and you choose some infinite small part of it. And only the threads can be classified into 3 classes. One is threads inside A, and one is threads that coming out from A bar to A bar. These 2 kinds of threads never intersect with this RT surface, but the threads that coming out from A to A bar intersect with this RT surface once. As we calculated before, in this case, you count the number of threads that intersecting with any segment on this RT surface. It will always give you 1 over 4g multiplied its normal vector. So this result does not depend on the choice of sphere. The position of this A and the size of the sphere is independent, and it always gives you 1 over 4g. So the number of threads that intersect with this segment is just 1 over 4g multiplied the area of this this area element. Note that any area element in the bar can always be embedded in some RT surface or hemisphere. So for some area element with some normal vector n, okay, there is a unique hemisphere that is tangent to this area element at this point, a unique one. So in some sense, for any area element, you can always calculate the number of PE threads that passing through it by embedding this area element on a hemisphere. And the answer is always 1 over 4g. So it seems that this result applies to any bar area element. And actually, you can do the calculation in this way, not only without this reference spherical regions. We just calculate this doing integration of x over the whole boundary and takes absolute value. You always get also 1 over 4g. So in this case, you do not need a reference spherical region, and you do some direct calculation, you will always get this value. So, for example, if you consider some line element in the bar here with direction here, you can draw some RT surface that is tangent to this element here, which is an RT surface of a single interval, and all the threads that intersect with this area element is this set of threads, which was calculated before. So this thing. Okay. So it tells you that the block is in some sense a close made of those PE threads, but this close has some property that you can cut this close at any place along any direction, and the number of threads that is cut by this cedar is always proportional to the area of this cut multiply 1 over 4g. It does not depend on where you cut this close or along any direction. So in some sense, the AdS space is covered by the PE threads uniformly anywhere. Okay. With this understanding, you can also consider some arbitrary surface in the bar, which do not have to be the RT surface of any region, and because the area element that intersects with the bar PE threads network is always some 1 over 4g multiplied the area, then the number of intersections between this curve and the bulk PE network is always the area of this curve over area of this curve multiplied 1 over 4G. So the conclusion is that the density of intersections with the PE threads at any point is always 1 over 4G. In other words, the AdS space is covered by PE threads uniformly. Okay. Then we reproduce the RT formula. So for an arbitrary homologous surface for some boundary region A, the number of intersections with the PE threads is proportional to its area. So we just use directly apply this conjecture. For some boundary region A, you consider an arbitrary homologous surface, and the number of intersections between this homologous surface and the bulk PE threads is always proportional to the area of this homologous surface multiplied 1 over 4G. And if you minimize the number of intersections, you minimize the equivalent to minimize the area of this homologous surface. So in some sense, you reproduce the RT formula, exactly the RT formula. So in this sense, you get some independent reformulation of the RT formula without knowing the RT surface in advance. Again, you can also reconstruct the length of any bulk curves, as we said. The length of this bulk curve is again given by the number of intersections between this curve and the bulk PE threads. So this reconstruction is not confined on the RT surface, but for general geometrical surfaces. Okay, then it seems interesting, but in this case, if you cancel this 1 over 4G and this the coefficient of central charge, which is related to the Newton constant here, you get actually some pure mathematical formula. Because this 1 over 4G makes it entropy, and this C over 6 makes it some partial entropy. And there's a cancellation between this 1 over 4G and the C over 6. Actually, if this coefficient cancels, actually this is some pure mathematical statement. So actually this statement is, just notice that this statement is exactly the so-called cross-term formula in mathematics. So in mathematics, you can also reconstruct the length of some bulk curve. For example, in two-dimensional flat space, you have some arbitrary curve in the plane. You want to calculate the length of this curve. Actually, you can use all the geodesics. In this case, this geodesic is just the straight lines. So you consider all the straight lines in this plane and count the number of intersections between these straight lines with this curve and do integration. In this case, the space of geodesics is described by these two parameters, which is P and phi. P is the distance between this straight line and the origin point, and phi is this angle. So you use P and phi to parameterize the space of geodesics, and then you count the number of intersections between this straight line and this curve, and do an integration. Actually, you will find that the cross-term formula tells you that the length of this bulk curve gamma is exactly given by this counting of number of intersections. This statement in flat space actually can be extended to Riemann manifold. For example, in this case, you consider some Riemann manifold and some surface sigma in this Riemann manifold, and you use some d gamma to be the measure of the space of all geodesics. As we said, that you always have to define the density of the geodesics in the Riemann manifold. And the density of geodesics is hidden in the measure of this space of geodesics, which is given by this way. In mathematically, there's some requirements, which is that the measure should be invariant under some coordinate transformations, which in general can be written in this way. It's d minus 2 form, which is you can choose some coordinate 1 surface and consider symplectic structure on this surface. And this symplectic structure is exactly this so-called kinematic measure, which is the measure of the space of geodesics. And you do an integration on this space of geodesics and count the number of intersections between this surface sigma and an arbitrary geodesic. This n is just the number of intersections, and do integration with some coefficient. This is exactly the same thing we did. You count the number of intersections between this sigma and all the bulk geodesics. So this number of intersections will reproduce the area of this surface. So let's go back to the special case of the AdS space. In this case, the space, the measure of this geodesic space can be given by this formula, where you use P as this. It actually can be parameterized by 2 endpoints of the interval. You start from this general formula, but P is given by some differential between of this geodesic length and the other endpoint, and so this measure becomes these x1 and x2, where x1 and x2 are the 2 endpoints of the geodesic. And then you find that this sigma, you plug in the geodesic length of any 2 boundary intervals, you get that this d sigma is proportional to this value. So in some sense, you find that the Crofton formula tells you that this kilometric measure is given by this, and if you do the calculation, you find that this formula is given by exactly the 2-point PE. So in some sense, the 2-point PE is exactly the measure of the geodesic space, which is originally claimed by us that this 2-point PE characterizes the density of the geodesics. So in this sense, we get some equivalent expression for the Crofton formula. So it's so you made a big effort to do some physics, but eventually you find that mathematicians always done this before in many years before. So yeah, it's correct, and our formula actually just gives some physical interpretations for this Crofton formula in terms of entropy quantities in AdS CFT. So essentially, this Crofton formula at least confirmed our consideration is right in Poincare AdS, and eventually you can extend our story to more generic space-time. I mean, go beyond Poincare AdS based on this Crofton's formula, because this formula is much more general. It does not only apply in Poincare AdS. So the next step is that you just interpret all the bulk geodesics as 2-point PE, and if you can get the information of the measure of the geodesic space, you can, in some sense, reproduce the boundary PE structure using this Crofton formula. Okay. So I guess I'm almost here. So give a summary. The static AdS space is uniformly covered by PE threads. Hence, we can interpret the area of any geometrical quantity in terms of number of PE threads passing through it. Mathematically, this context is a special application of the Crofton formula in the context of AdS CFT with entropy interpretation for all the bulk geodesics. The contribution from outer threads to entanglement gives us some new understanding about the entanglement structure of holographic series. And the future directions is that how to go beyond the Poincare AdS, for example, black holes and the space-time with matter fields, are now AdS space-time. how to go beyond the static scenarios and how to reconstruct the time direction in terms of the boundary entanglement structure. And Coin model of quantum gravity can be based on the tensor network of P threads. The last point I want to stress is that the P threads network in the path is in some sense a continuous limit of a new tensor network that can be used to describe AdS space. So it does not has the it is a natural continuum limit. It's continuous, not a continuum limit. So it solves a fundamental drawback of previous tensor network models. Okay. Okay, thanks.
Thank you very much for inspiring talk. Any questions? We asked a lot of questions along the way. So,
okay.
So if not, let's thank the speaker again.
Thanks.